Let's talk polar compounds. When I say polar, you should think of things like magnets or charge or the Earth. It's got a north pole and a south pole. Polar means that we have opposite ends, ends that have opposite effects. And with a magnet, if you remember, a bar magnet has a north pole over on one side, and the other side is a south pole. And if I bring another magnet up next to it, one of two things can happen depending on the magnet. If it's another north pole, then these things push apart from each other, and if it's a south pole, then they pull towards each other and they attract. So polar things have opposite sides, and remember, opposites attract. Why do we care about polarity if we're talking about atoms and molecules? Well, it has to do with a covalent bond. Remember, in a covalent bond, you've got the nucleus of the atom hanging out here, and it's got lots and lots and lots of positive charge. And around that, in the cloud of electrons, we have electrons, right? And there's an attraction between these positive protons and these negative electrons. The further these electrons are from the nucleus, the less that attraction is, just like when you pull magnets far enough apart from each other, they don't interact. But if I have another one of these atoms, so I'm going to go ahead, join these guys up, and clone them, so I get another one of these atoms. All right, so now I have two atoms with their protons in the middle, their positive nucleus, and their electrons floating around the outside. Well, if these are close enough to each other that their electron clouds start to overlap, then it turns out these electrons are attracted to both this nucleus and that nucleus, and that's what we call a covalent bond. But these shared electrons are not always shared equally. Now, these two atoms are identical, so they would share electrons equally. Neither protons can pull electrons harder than another. But imagine if we had something like fluorine. Okay? Fluorine is element number 9 on the periodic table, which means fluorine has 9 protons in the nucleus. Okay, so it's very, very, very positive. I'm going to go ahead, I'm going to say 9 plus. There's the nucleus. It's got one inner layer of electrons and one layer of electrons here, which means it's got a big nucleus and not very many electrons, which means it can pull really, really hard. Okay, pull hard on electrons. Now, if we have another atom, say not fluorine, I don't know, something like hydrogen, okay, hydrogen has got one little proton and one little electron, and those two charges exactly balance, and that one little proton can't really pull very hard. So if these two things get together and they form a covalent bond, the electron cloud in general is going to get shifted away from the hydrogen nucleus and towards the fluorine nucleus. So the little hydrogen nucleus is over here on the end, and the fluorine nucleus is here in the middle. The electrons are all pulled up over here. And what that means is all the negative electrons are piled up on this end, and that positive proton is kind of hanging out over here. That means I have a polar substance. Just like I had a magnet that had a north and a south pole, now I have a molecule that has a negative side and a positive side. It's got these partial charges on either end. Sort of like an ionic bond, except it's really more the electron cloud is shifting than electrons themselves are being transferred. So I have these polar things. Not everything is polar. Some things are polar. Okay? So if I have a polar molecule, it's got a positive side and a negative side because of unequal sharing of electrons. So polar molecules have a positive and negative side due to unequal sharing of electrons. Big whoop, right? Who cares? Why does this matter? Why do we care about polar things? Well, it turns out this is an incredibly important concept in biology. There's a lot of polar molecules, and if we didn't have polar molecules, we would have a hard time building a cell membrane. Okay? And we'll talk about that in more detail later. For now, I want to focus on what happens if we have something that's polar and something that's not polar. So if I have a polar molecule and it's got positive on one side and negative on the other, and I have a whole bunch of these. Let's go ahead and make this one thing and get a whole bunch of them. And we'll go ahead and turn on infinite cloner. Okay, so I can get a whole bunch of these guys. Okay, all these little polar molecules, if they're all floating around, they will actually line up in a very specific pattern, right? The positive side is going to line up next to that negative side, and the positive side is going to line up next to that negative side. And these things are going to want to stick kind of together, so we get positives next to negatives, sort of like ions in a crystal, okay? Not quite as tightly bonded as that because it is just a polar partial charge, not a full charge like in an ion, but they'll line up in a very specific way. So that's because the polar molecules attract other polar molecules. So polar attracts polar. Okay? Now, what if I put a molecule in here that's not polar? What if I put a molecule in here that's got no positive or negative side? It's just nice and evenly distributed charge. Okay, so this is my nonpolar molecule. It's got no pluses. It's got no minuses. It's just hanging out here. Well, what happens when I put a whole bunch of these together in here? Are they going to stick with those other polar molecules? And the answer is no. There's no attractive force between them. But if there's another polar molecule here, it's actually going to kick this thing out of the way so it can go line up and be with its friends, be with its polar and non-polar or polar buddies, so it can get its plus and its minus lined up. Okay, it's just like if I had a bowl full of magnets and I threw a BB in there, the magnets are going to stick together and the BB's not going to stick to anything. Okay, so when I mix polar in with or nonpolar in with polar, they don't mix very well at all. So nonpolar does not stick to polar. Nonpolar does not mix with polar. Okay? Now this is why oil and water don't mix. You can shake them up and you can stir them up, and at the end of the day, they are going to separate back out. Water is a very, very polar substance. Water has an oxygen atom, and oxygen is a fairly big atom. It's right there next to fluorine as far as the little elements that we are dealing with go. So it's got an 8+ in the middle, okay, and it's got those 2 layers of electrons around it. So it's got lots of protons and only 2 layers of electrons. And then we've got hydrogen with its 1 proton and another hydrogen with its 1 proton and 1 electron. Just like fluorine can be an electron hog, oxygen can be an electron hog. So this is going to pull the electrons in closer to it, and this Mickey Mouse shaped water molecule has a slightly positive charge over here with the hydrogens and a slightly negative charge over here with the oxygen. It's a very polar molecule. Okay? Oil, on the other hand, is just a bunch of carbon and hydrogen atoms, and carbon and hydrogen bond in a nice uniform way, and all those carbon atoms are identical, so they share pretty easily. Carbon's got 4 protons, 6 electrons, and it's a fairly non-polarizing atom. It doesn't have a huge pull for electrons, so these are all non-polar things. So when I bring this oil molecule in here, it doesn't have a charge, so it's not going to stick to the water. So we shake it all together, and yeah, we can mix them for a minute, but then the water molecules, because of their attraction for each other, are going to stick together and push the oil out, so it separates into layers. So polar mixes with polar. Nonpolar will actually mix with nonpolar because they don't care. Nonpolar mixes with nonpolar. Okay? But we're not really going to have polar and nonpolar get together. Now, where do ions fit in all this mess? Well, an ion, remember, actually has a full charge. It's not a neutral thing. It's a full positive or a full negative, or maybe even a full plus or 2+ or 3+, and a full minus or 2- or 3-. What are they going to stick to? Well, they'll stick with polar things, right? If I have a polar water molecule with its 2 Mickey Mouse ears that are slightly positive, that polar water molecule will actually align itself around this negative charge, and then it'll line up the other way over here. Okay, so the water molecule can stick to a positive thing or it can stick to a negative thing. It doesn't have to be polar. It can have just one charge or the other, and the polar things will still stick to it, which means ions dissolve or dissolve in polar compounds. Okay? So that leads us to this whole like dissolves like. If it has a charge or a partial charge, that is to say, if it's ion or polar, they'll get together. Nonpolar and nonpolar get together. Okay? But those two don't mix very well. So like dissolves like means the charged things get together, the non-charged things don't, and this actually leads to some really cool things in the cell and how our bodies are able to function and do cellular processes and contain certain things in certain places. So we'll look at a phospholipid bilayer, which has both polar and non-polar sides, and it can arrange itself in a nice cool cell membrane. Okay, that's for a later lesson, but right now you should understand that a polar thing has a positive side and a negative side, and it will stick with other positive and negative things, and it will push out non-polar things.